All right, so back to this problem. Yeah, let's take a look at this triangle. Let me see here. I'm going to see what this is. 0, 0, triangle with these vertices 0, 0, 1, 0, that's right here, 1, 0, and 1, 1. Okay. All right, so this is the region. So here I am. Look, right, you're right. Look, I'm doing the average value of the function. So it's this formula, which means, like we sort of said, it's the volume divided by the area. I'll tell you what, can we go ahead and get the area without doing a double integral? Can we use a little geometry on this triangle, please? The area is 1/2 the base and 1/2, right, 1/2 base times height. I think the base is 1, the height is 1. I think the area of this triangle is 1/2. Cool. The area of the triangle is 1/2. Okay, so that's the area of my region R. Okay, so region R. Okay, so cool. That's kind of the denominator here. But now I need that volume. And so in order to do that volume, I really do have to do a double integral here, I guess. So I need the double integral over this region. And what function am I integrating? Oh, I'm integrating this function. And, you know, it's my choice now, dy dx or dx dy. I don't think it matters much. I think I'll do dy dx. So now I have to look at my picture and I have to set up the bounds for this double integral. And I think the bounds are for y. Well, you know, one thing I've glossed over here is I guess I need the equation of this line. Of course, it's real easy. From 0, 0 to 1, 1 is that's a very famous diagonal line called y equals x. So I think the bounds for y are 0 to x. From this y value to this y value. Y equals 0 to y equals x. The bounds for y are 0 to x, while x goes from 0 to 1. Thank you, thank you, thank you. Cool. That'll be the volume. Now wait a minute. I'm sorry. I'm not that sorry, but I'm. What this question wanted was this thing called the average value. Okay, so the average value, according to this formula, let's get back to this formula. The average value is that volume divided by that area. Or if I wanted to talk like this, 1 over the area. So, and we already calculated the area to be 1/2. So it's 1 over 1/2 times this double integral that I need to work on here. 0 to 1, 0 to x, 1 over xy, dy dx. So crank this all out with the 1/2 out front, actually the 1 over 1/2. And by the way, 1 over 1/2 is actually a 2. So crank this out with that 2 out front and you'll have the average value. Right. We could try to finish this. This is a little funny. This integral looks funny to me. How am I going to integrate this with respect to y? I guess I know the answer. It still feels funny, but I guess I know the answer.
Is it the U-Substitution?
Well, you could call it a U-Substitution. So if you let u equal x plus y, again, x is a constant, y is the variable. So if you let u equal x plus y, du is just dy. It sort of turns this into a 1 over u du. You hear me? So I'm doing this in my head kind of because I don't really need to write all that down. If it's a 1 over u du, I think the integral is? Well, that's the ln of u.
Oh, right, du over u is.
Du over u, 1 over u du. It's the ln of u. Yeah, it's a 1 over. So okay, the inner integral is the ln of x plus y. Hang on now. That's the inner integral, I'm telling you. And now what my bounds are 0 to x. Is that what's going on? And I'm plugging that in for y. Yeah. Okay, so I get the log of 2x, because if I plug an x in there, it's x plus x, minus, and when you plug in a 0, you get the log of x. All right, listen, this is cool. Don't forget about this 2 out here. But this is the answer to the inner integral, which I think I'm going to do fancy log work here. What can I do with fancy log work? If I have the subtraction of 2 logs, I can write that as 2x over x. Did you know that? That's good old log properties.
This is 2.
And that's just the ln of 2, which is just a number. Dude, this is so awesome. Now wait a minute. This is the answer to the inner integral. Now I have to integrate this with respect to x from 0 to 1. And don't forget, there's a 2 out front.
So just 2 ln 2.
Well, I think you could be right. First of all, when you integrate with respect to x, this is just a number. So you're not integrating ln, it's just a number, and so it's a number times x. So you're right, it's x times this number. When you plug in 0 to 1, you plug in your 1. Yeah, you're totally right. The answer is ln 2. Don't forget this 2 is out front, so there's the answer, 2 ln 2. That's the average value. Hey, using fancy log rules, you know what somebody else might call that something different. You know what they would do? Using fancy log properties.
2 to the second?
Yes, they would move that 2 up there like a power, and they would call it ln of 2 squared, which is ln of 4, maybe. Maybe. It's the same thing, actually. Yeah, that was kind of fun. Average value. Just another use of this double integral, I guess. It's really volume over area idea. One of my favorite sections is next. 14.3 is next. We start when we start integrating over these circular regions, the x's and y's, rectangular coordinates are not nice for circles. And so we get to switch to polar coordinates. So that's what's coming up in 14.3. We'll get out of x's and y's. We'll switch to r's and thetas. I might have to give you a quick little 10 minutes review of polar coordinates and how they relate to x's and y's. But that was what we're polar coordinates. We studied polar coordinates right at the end of Cal 2, in Chapter 10 at the end of Cal 2. About the last thing, we did some polar coordinate stuff. So it's been a while. But I'll remind you of some polar coordinates, and we'll switch into polar coordinates next time, I guess. So we'll quit today. You can try some homework in 14.1 and 14.2.